Hello and welcome to my office. This is going to be part one of a multi-part series. I'm not quite sure how many chunks I'm going to break it up into. It was 2 hours of edited video when I filmed this intro, and there were a couple of sections left to do. So you're looking at a treat. It's going to be probably 3 hours long in total. We're going to be going all the way back to my roots as an embedded programmer. In 2008, when I was a college freshman, just starting to play around with microcontrollers, and got a couple of PIC samples and borrowed a programmer from my friend down the hall in the dorm and started building a computer-controlled automatic rubber band gun turret. Fast forward a couple of years, I started getting into embedded security and semiconductor reverse engineering, and in 2011 the PIC12F683 became the first part that I broke the read protection on. And I've always wanted to go back and finish the job and go do a more extensive deep dive and circuit analysis on this part. At the time, I didn't really have the lab capabilities or the skills. Fast forward a few years, I ended up getting a job in the embedded security industry, doing, among other things, semiconductor reverse engineering professionally. And so I've had a bit of time to go get a lot better at this sort of analysis. My home lab has massively improved in capabilities. And so I've decided to go back and finish the job. I am still going to be doing this entirely in my home lab. I do have access to all sorts of fancy toys like plasma etchers and a dual beam SEM fib and a fancy multi-axis polisher at work. We're not going to be using any of those resources. We're going to be doing this with purely optical microscopy and wet etching and generally capabilities available to a well-funded private individual. And before we get too deep into the analysis, a little bit of background about the part itself. It is a 8-bit microcontroller made on Microchip's 160K process technology. This is an in-house process made at one of their fabs in Oregon with 3 aluminum metal layers and roughly 350 nanometer feature sizes. It clocks at a maximum of 20 megahertz at 4 clocks per instruction, giving an effective processor speed of 5 MIPS. Firmware is stored in onboard flash memory with 2048 words of 14-bit instructions. There is additionally 128 bytes of SRAM and 256 bytes of data EEPROM. The EEPROM is runtime programmable by firmware. The flash can only be programmed externally. So the first step in our analysis is going to be getting a better understanding of the device package. The particular part that we're looking at is going to be in what's known as a DFN, or dual flat no leads package. The same silicon is available in other packages, but this is one of the least expensive, and if we're just going to destroy it anyway, why choose something that costs more? Plus, it's smaller and there's less material to remove when we're trying to actually get to the silicon. So, seen from the top down, roughly what this looks like is we have a bunch of solder terminals here. Doing a terrible job of drawing 8 of them, but please excuse my horrific artwork. My 4-year-old scribbles on the walls are probably demonstrative of more artistic talent than I have, but I'm going to work with what I can. And so we have the actual silicon in the center of the device. We've got the solder terminals here. I'm just going to try and redraw these just a little bit more even. And so we have the actual silicon somewhere in the middle of the device. This is going to be mounted to a copper paddle. And then we have the actual solder terminals on the perimeter. And so somewhere on the outside of the device, let's just notionally say we've got 4 in a line. This is not how the actual silicon is laid out, but just for illustrative purposes. We've got a series of bond pads on the die where the actual signals come in and out of the silicon. And then there are wires coming from these points out to the actual solder terminals. So we're just going to draw that like that. There are other types of package construction besides wire bonding, but wire bonding is by far the least expensive and also the most common in low-cost devices. So this is what we're expecting to see inside here. And so in order to better understand how the device is packaged, we're going to want to do a cross-section. And so this is from the top down, looking through the package into the circuit board. We can also imagine this in cross-section. We've got the outline of the overall device. We've got this copper paddle here. Let's actually draw that a little bit more inboard like this. We've got the solder terminals here, and then we have the silicon on top, and this is attached to the paddle by some sort of conductive adhesive. Usually it's an epoxy with silver particles filling inside it. And then we have the wire bonds, which I'm going to do in red to stay consistent. So the wire bonds are going to come out from here and out to here. And so in order to get a better understanding of how the device is put together, we can go and do a mechanical cross-section of the device. There are other fancier tools available if you've got a nice lab and you can X-ray it or CT scan it or whatever, but in my case the device costs a couple of dollars. I have a whole tape full of them. I don't have a CT scanner, I've got a polisher. So we're going to go do an old school mechanical cross-section. And in this case, we're interested in trying to see the wire bonds. So we ideally would want to get a cross-section roughly along this plane so that we can see the bond wires and specifically see the bond pads and their connection to the die. So the one problem with doing a polish from this perspective is that it, best case, will give us two bonds in cross-section, and that's if this bond pad and this bond pad are at the same height. We don't know the actual bond out of the device yet, and so there's a very good chance that some of these bonds may be at different positions, north-south, relative to others. But generally, along an edge of the device, the wire bonds are all in a line. They're usually essentially as close to the perimeter of the die as you can get. And so what I'm actually going to do in order to maximize the chance of getting potentially a couple of bonds in cross-section is we're actually going to do the cross-section from this plane, looking in. And so we're going to want to section this way rather than in this view, which would be like this, obviously lower down. But so rather than sectioning this way, we're going to section this way, and so ideally try and get a couple of bonds. This does mean that we're not going to be getting the solder terminals in cross-section, but we are going to be getting the die attached paddle, we're going to be getting the actual silicon, we're going to be getting the adhesive layer between them, we're going to be getting the wire bonds, and then obviously lots of the epoxy glass filled molding compound. Right now I'm taking one of the samples off of the tape. This is a PIC12F683 in the industrial temperature range, the 4x4 millimeter 8-pin DFN package, date code 2321, and the last line 9BW is a lot number or something like that. And so the sample is going to get mounted edge on in this little plastic clip for cross-sectioning, and we're trying to polish in through 4 of the pins and ideally get all of the wire bonds in cross-section so that we can look at the package construction as well as the metal layer stack-up of the device and better understand how it's put together. And this is going to then be embedded in an acrylic resin for cross-sectioning. So now we're over at the wet bench, and the next step is going to be to actually take the sample and put it in the mold so that we can embed it. We start with mold release spray so that it doesn't stick. This is just a standard epoxy mold release. It works just as well for acrylic. Shake off any extra. All of the measurements are done by weight, makes things nice and easy. We don't have to worry about trying to measure precise volumes, especially because the powder is pretty fluffy and very bulky. You do want to be careful doing this in a fume hood. The particulates do try to blow around a little bit in the airflow, so try and make sure that you aren't pouring a long distance from your scoop into the beaker. Otherwise, it blows all over the place and makes a big mess of your hood. Ask me how I know. But it is a good idea to do this in a fume hood just because otherwise it makes a mess and you don't want to get the particulate airborne. It's not the friendliest thing to inhale. And now this is the liquid part. So the way that this resin system works is that the powder is acrylic particulates plus I believe it's an organic peroxide-based curing additive, and then the liquid is additional uncured monomer, and so when they're mixed, you get a solid resin with the monomer cross-linking around the existing particulates. And one of the nice things about this system is that you do have a pretty forgiving mix ratio. It's not like epoxy where if you get things a little bit off, it's not going to cure properly. And now we've got the components measured individually, so we can put the sample in the mold and then begin to actually mix the resin. You do want to be a little bit cautious mixing it and not stir too vigorously. Obviously, the components do need to be thoroughly mixed, but if you stir too aggressively, it will incorporate air into the mixture, and then you get bubbles, and you can get voids in your mold. This resin does cure in only a couple of minutes, and so it doesn't have as much time to degas as something like a low viscosity epoxy. And while you can do it in a vacuum chamber, it cures fast enough. I don't recommend it. So in this case, we're trying to get the sample buried about 6 millimeters of total depth. That's about the right height for the sample holder that I'm using. If you go too deep, it just means you have to polish off more material afterwards, and it's a waste of time and abrasives. And then I did get one little air bubble there, so I'm just going to pop it real quick with a toothpick so we don't get a void in the mold. So while we're waiting for the resin to cure, I'm going to prepare the polisher with a P180 silicon carbide abrasive sheet. The goal here is just going to be to rough thin the sample, remove any of the meniscus on the edge of the sample, get the surface nice and flat so that when we're doing thickness measurements later on, we've got a baseline to measure against. And now it's been about 15 minutes and the sample has cured, so I'm going to remove it from the mold. And we can see that there's a little bit of a meniscus along the perimeter, as well as a couple of sections sticking up near the center where it looks like some of the resin had stuck to the side of the mold as it was poured in. So now I'm going to peel off a little bit of the loose stuff that comes off by hand, and then prepare to polish off the rest. Just get a little bit of lubricant on here so we don't have too much dust and it doesn't overheat. And get it mounted up in the fixture. For the first pass, I'm only doing 2 minutes. There are going to be several more passes off camera. With the silicon carbide papers on this polisher, you do want to limit the duration of a single polishing pass to around 2 minutes. If you go too much longer, then you start getting uneven wear and surface becomes very non-uniform. And now it's been a couple minutes of polishing. The sample has been removed and rinsed, and we're looking at the back side still. The surface is pretty uniform. There's one little spot here where there's a small depression, but it's not enough to worry about polishing any further. The important bit is that right behind the device, we do have a flat surface we can use as a measurement data. And now flipping over to the front, we're going to take a thickness measurement of the whole sample. The actual chip is about 4 millimeters thick, and the entire sample measures about 6, so we have approximately 2 millimeters of resin on the back side. Back onto the polisher, we're going to do pretty much the same thing on the front side, and the goal here is going to be to remove most of the 1 millimeter of package before we get to the silicon. We want to take off probably around 700 microns and then switch to finer abrasives as we get closer. So here we are after a bunch more polishing. I went through P180, P400, P800, P1200, and then 2500. Probably went to 2500 a little too soon. I ended up spending a couple of hours there, but silicon is really brittle, and especially with this sort of system, it is very easy to crack it and cause fairly large amounts of damage that you have to polish quite a bit into to remove. And so whenever I'm doing cross sections, I would rather go slowly. I'm not in a rush, and letting the machine sit there and run for an hour doesn't really cause a problem for me. And so, anyway, at this point, we're now down to just the very edge of the bonding area, and it's getting to the point that the details we care about are a little small to see under the stereo microscope. So we are going to switch over to the big one. We're going to go and get the sample roughly positioned on the stage and get a bit more 20x objective, and then get at least a rough idea of where. So we can see the sample is a little off level. I didn't bother to get it precisely positioned since we're just doing a quick in-process view to see how things are going with the polish. There's still a bunch of scratches. That's to be expected at this stage of the polish. We're not expecting to be at a perfect finish until we switch to some finer abrasives, but we're pretty close to where we want to be. The ball bonds are now in section. We have not quite got to the center line of the wire, but we're in the wire bonds, and we just want to go back probably another 5-10 microns to get into the wire itself, and we'll be at a perfect stopping point. And zooming in a little closer, we can see we've got 3 aluminum metal layers and then the copper ball bond on top of that. And now fast forward another couple of minutes, and we have gone into the bond wire itself. So we're now not quite centered, but there is wire visibly sticking up out of the top of the ball, and so I'm going to call this a satisfactory stopping point. So at this point, we've gotten to the point of interest. We're not trying to remove a lot of material. We just want to improve the surface finish. So I've got this polishing cloth, already has some 1 micron diamond suspension on it from last time I used it. I'm just going to squirt a little bit more on there. And we're going to add a little bit of lubrication since the fluids in the previous diamond paste have probably dried up. It's been a week or two. And now we're just going to mount this up, and we're going to give it just probably maybe 2 minutes and see how it looks. Again, we're not trying to take a lot of material off, we're just trying to get those deep scratches out and get something ready for a final polish. So it's now been probably 10 or 15 minutes at the 1 micron diamond, and the surface is looking pretty good. We just need to give it that last final shine before we can go get some really pretty images out of it. And for that, I'm going to try some colloidal alumina, 50 nanometers. Silica might actually work well as well. In my experience, alumina gives good results on copper. There is a little bit of copper in the die attach paddle, and so for that reason, I'm going to try to use the alumina, and we're going to see how it all works. We should only need that 1 squirt here, and I don't think we're going to have to add any more. This is a fairly short run. I'm probably just going to do maybe 3 minutes and see how that works out. So we're done with the final polish, and it's just going to be a little bit of cleanup, and we can see how it turns out. Definitely distilled water here. We don't want to use tap water to avoid getting any sort of mineral deposit, especially around here. My tap water is pretty hard. And then blow all of the water off of the top surface. We don't want to be touching the surface that we're imaging with anything now that we have this extremely high quality finish. And we're going to take a look at this. I'm probably going to sonicate it, but I'll take a quick look under the microscope just to see if that's necessary. And then we're just going to clean up this polishing pad as well. These are somewhat expensive, and I like to reuse them where possible. It's a little tricky to get all of the suspension out of it and get it nicely dried so it doesn't go moldy. I have lost quite a few to mold over the last couple of months, but I at least attempt to preserve them when I can. So here we are after the final polish. I took a couple of minutes to get it leveled and locate all of the corners so we can do a large area automated scan. We can see we've got much nicer surface finish here, and all of the wire bonds are clearly visible. We've got a nice view of the plating on the underside as well as the die attach epoxy. And we can see I've already located the bottom left, the top left, and the bottom right corners. And now I'm going to run an automated scan of the entire die so we can get a nice high resolution image of the whole thing that we can look at later. Now that the scan is finished up, we're going to take a few close-ups under the 100x objective. Here is the bottom left corner of the thermal pad. We can see that the copper paddle has a tin plating on the bottom to aid in soldering. Then going up to, this is the bottom left corner of the die, looking at the silver epoxy that is holding the die to the paddle and providing both a thermal and electrical connection. Moving up to the top left corner, now we're at the seal ring. This is the periphery of the die and makes sure all the metal layers are firmly anchored and we don't have any delamination. There's a little bit of a space to the left so that the saw can have a little bit of tolerance for positioning and we don't risk cutting into the seal ring if the saw is slightly misaligned during dicing. And there's clearly poly, then 1, 2, 3 aluminum metal layers. Zooming in a little closer, we can again see the 3 metal layers, and barely at the limits of optical microscopy, but there is a slight angle visible on some of the tracks where the wires are a little bit wider at the bottom than the top. This is characteristic of RE etched aluminum. And now we're taking a close-up of one of the copper ball bonds. These are formed by taking a small copper wire and striking an arc to it in a reducing atmosphere to melt the tip of it into a sphere. And then a needle presses this down onto the bond pad, and ultrasonic vibrations are applied to essentially friction stir weld the wire onto the surface. And we can see there's a little bit of squeeze out at the top metal layer where when the ball was applied, it slightly deformed the aluminum. And then looking up towards the top, we see the main diameter of the wire, and below that is the deformed area where the ball was squished out and flattened. This right here is the inside diameter of the needle, and so we can see that as the needle pressed the ball onto the pad, it squished out to the sides and then also squished up a little bit inside the needle. And now we're looking at another ball bond that is a little bit further into the sample because the polish was not perfectly level, so we can see that we're still in the bond pad. We've got all 3 metal layers visible, but we haven't actually got into the ball itself. It's still slightly buried through maybe 10-20 microns of molding compound. And then moving to the right side, we can see the last little bits of power interconnect, and then a couple of other signals near the perimeter, and then the seal ring on the right side of the die. And I was very happy with the quality of this corner. The longer polish at the P2500 definitely made a big difference on surface quality. There's no chipping or cracking or anything visible at the corner. It looks flawless. And then moving down to the bottom right, we've got a little bit more of the die attached. This is again the bottom right corner of the die attaching to the paddle, and we can see a little bit of the surface roughness on the paddle. It's probably etched or sanded in some way to increase the roughness so that it attaches more firmly. And now going down to the bottom right corner of the thermal pad, we can see that the plating is actually extending out a little bit over the molding compound. So this is interesting. It means that the unplated paddle was first attached to the mold, and then after the mold was applied, then it was plated. And with that, we're done with part 1 of the video. Stay tuned for part 2 coming out very soon, in which we're going to depackage the devices and start actually getting a look at the circuitry. I hope you enjoyed, and see you next time.